One type of redwood tree has an average height of 65 feet when it is 20 years old. If the tree is more than 20 years old, the average height, h, can be modeled by the function h equals 1.95 times the quantity of a minus 20 plus 65, where a is the age of the tree in years. Which statement about this situation is true? Okay, before we even look at the answer choices, let's look at the equation carefully and understand the equation, because all these answer choices are designed to confuse us. So let's cover those up right now and not even pay attention to that right now. Okay, so we have h equals 1.95 times the quantity of a minus 20 plus 65. Let's figure out what is what in this equation. So it says a is the age of the tree in years. Alright, so I'm going to go ahead and label this. And actually, I have enough room here. This is the age of the tree. And it's in years. I'm going to go ahead and put that too. Okay, and let's look at the problem and what's going on here. It says one type of redwood tree has an average height of 65 feet when it's 20 years old. So do we see a 65 in here? Yes, we do. It's right here over on the end, and this is a linear situation. There's no exponential, there's no squared variables or anything. So we can go ahead and kind of be thinking along the lines of this. Alright, so this is our independent, this is our dependent, this is our rate of change. And what is the b? The b is the starting value. Okay, so basically they're saying they're starting this situation when the tree's 20 years old, because that's the average height at 20 years old. So this is my starting value. I'm going to put SV for that, and I'm going to go ahead and put that it is, I'm going to fix my autofocus here. I think that did it. It's basically 65 at 20 years old. So I'm going to say that's at 20 years old. So what's going on in the situation? They're starting at 20 years old, and then this is the age of the tree in years. But how come they're taking away 20? Because they're not multiplying the age by 1.95. They're multiplying the current age, but they're taking away the first 20 years. Because the first 20 years height is already accounted for right here. In the first 20 years, the tree is going to be 65, an average height of 65 feet. So what they're doing here, they have the age of the tree, but they're taking away 20. So this is the age of the tree, the number of years the tree has grown after the first 20 years. Because after those first 20 years, there's a ratio of 1.95 feet. And they don't tell us much about the ratio, but we know that the m, or the rate, is always our change in y over our change in x. What is our y and our x? Our y is this and this. What are those in the problem? They told us that this is the height. So the height depends on the age, because y always depends on x, right? So this is the height, and this is the age. So they're saying the height depends on, first of all, the first 20 years of age, the height's going to be 65. And then what happens, the next years after the 20 years, you take away the 20, and you're multiplying those other years by 1.95. There's your ratio. That's like your height per year ratio right there. Okay? So we've understood this equation, and we haven't even looked at the answer choices yet. And that's what I recommend, because answer choices are going to throw a lot of stuff out there just to be tempting and confuse you. But after we understand it, it shouldn't be too hard to find the right one. Okay, so choice A says, every additional 1.5 feet of length over 20 feet adds 45 years to the age of this type of redwood tree. Okay, I'm not sure where that's coming from. First of all, the big thing that's a red flag for me is it says that length is adding years, but our independent and dependent are the years is the independent. So basically height depends on age, but this one is saying that age depends on height. They're saying the longer it gets, the older it gets. And that doesn't make sense because the height is depending on the age. Okay, so we can say age doesn't depend on height. That's why this one's wrong. Alright, choice B. For this type of redwood tree, the average height increases 1.95 feet per year throughout its lifetime. Now this one's really close. Here's why it's not correct though. It is 1.5 feet per year. This is a feet per year ratio. But it's not times the total age of the tree. It's times the age minus the first 20 years. So this throughout its lifetime is the part that makes it wrong. Okay, it's not, this ratio only applies after the first 20 years. That's what's going on right here. You're taking away the first 20 years, then it applies to all the other years after that. Okay, how about choice C? Each additional year of age over 20 years adds 1.95 feet to the average height of this type of redwood tree. Okay, let's take a look at that. So, each additional year of age over 20, now this is the age, over 20, that part's right. You're taking away the first 20. So this is each additional year after 20, and you're multiplying it by 1.95. So far that looks really great actually. Okay, is there anything else that's wrong? Is this 1.95 really feet? Well, what is the ratio? It is years. It is the ratio is always change in y over change in x, right? That's our rise over run, which makes up our slope. It's height per year. So yeah, it does make sense. 1.95 feet per year. That makes sense. So I'm actually going with C. I think it's a great choice. Let's take a look at D. For this type of redwood tree, the average height increases by 65 feet for every 20 years of growth. 65 feet, okay. Well, it's the first 20 years is what they say. It's actually not every 20 years. The first 20 years is 65 feet. And then after that, there's this ratio they throw in for every year after that. So no, we cannot agree with that. It says here it's basically growing its most at the first 20 years, and then it goes by this little model here. So I can't say D is right. So I'm going with the correct answer, and it is C.